Shape memory polymers are polymeric smart materials that have the ability to return from a deformed state to their original shape induced by an external stimulus, such as temperature change. Properties of shape memory polymers: SMPs can retain 2 or sometimes 3 shapes, and the transition between those is induced by temperature. In addition to temperature change, the shape change of SMPs can also be triggered by an electric or magnetic field, light or solution. As well as polymers in general, SMPs also cover a wide property range from stable to biodegradable, from soft to hard, and from elastic to rigid, depending on the structural units that constitute the SMP. SMPs include thermoplastic and thermoset polymeric materials. SMPs are known to be able to store up to 3 different shapes in memory. SMPs have demonstrated recoverable strains of above 800%. 2 important quantities that are used to describe shape memory effects are the strain recovery rate and strain fixity rate. The strain recovery rate describes the ability of the material to memorize its permanent shape, while the strain fixity rate describes the ability of switching segments to fix the mechanical deformation. Where n is the cycle number, I micrometer is the maximum strain imposed on the material, and I micron p, n, and I micron p, n1, are the strains of the sample in 2 successive cycles in the stress-free state before yield stress is applied. Shape memory effect can be described briefly as the following mathematical model. Where EG is the glassy modulus, R is the rubbery modulus, FR is viscous flow strain and V plus or minus is strain for TTR. Equals triple shape memory equals, while most traditional shape memory polymers can only hold a permanent and temporary shape, recent technological advances have allowed the introduction of triple shape memory materials. Much as a traditional double shape memory polymer will change from a temporary shape back to a permanent shape at a particular temperature, triple shape memory polymers will switch from one temporary shape to another at the first transition temperature, and then back to the permanent shape at another, higher activation temperature. This is usually achieved by combining 2 double shape memory polymers with different glass transition temperatures or when heating a programmed shape memory polymer first above the glass transition temperature and then above the melting transition temperature of the switching segment. Description of the thermally induced shape memory effect. Polymers exhibiting a shape memory effect have both a visible, current form and a stored form. Once the latter has been manufactured by conventional methods, the material is changed into another, temporary form by processing through heating, deformation, and finally, cooling. The polymer maintains this temporary shape until the shape change into the permanent form is activated by a predetermined external stimulus. The secret behind these materials lies in their molecular network structure, which contains at least 2 separate phases. The phase showing the highest thermal transition, TPERM, is the temperature that must be exceeded to establish the physical crosslinks responsible for the permanent shape. The switching segments, on the other hand, are the segments with the ability to soften past a certain transition temperature and are responsible for the temporary shape. In some cases this is the glass transition temperature and others the melting temperature. Exceeding TTRANS activates the switching by softening these switching segments and thereby allowing the material to resume its original form. Below TTRANS, flexibility of the segments is at least partly limited. If TM is chosen for programming the SMP, strain-induced crystallization of the switching segment can be initiated when it is stretched above TM and subsequently cooled below TM. These crystallites form covalent Newt points which prevent the polymer from reforming its usual coiled structure. The hard-to-soft segment ratio is often between 5/95 and 95/5, but ideally this ratio is between 20/80 and 80/20. The shape memory polymers are effectively viscoelastic and many models and analysis methods exist. Thermodynamics of the shape memory effect equals, in the amorphous state, polymer chains assume a completely random distribution within the matrix. W represents the probability of a strongly coiled conformation, which is the conformation with maximum entropy, and is the most likely state for an amorphous linear polymer chain. This relationship is represented mathematically by Boltzmann's entropy formula S equals KLNW, where S is the entropy and K is Boltzmann's constant. In the transition from the glassy state to a rubber elastic state by thermal activation, the rotations around segment bonds become increasingly unimpeded. This allows chains to assume other possibly, energetically equivalent conformations with a small amount of disentangling. As a result, the majority of SMPs will form compact, random coils because this conformation is entropically favored over a stretched conformation. Polymers in this elastic state with number average molecular weight greater than 20,000 stretch in the direction of an applied external force. If the force is applied for a short time, the entanglement of polymer chains with their neighbors will prevent large movement of the chain and a sample recovers its original conformation upon removal of the force. If the force is applied for a longer period of time, however, a relaxation process takes place whereby a plastic, irreversible deformation of the sample takes place due to the slipping and disentangling of the polymer chains. To prevent the slipping and flow of polymer chains, cross-linking can be used, both chemical and physical. Physically cross-linked SMPs equals linear block copolymers. Representative shape memory polymers in this category are polyurethanes with ionic or mesogenic components made by pre-polymer method. Other block copolymers also show the shape memory effect, such as block copolymer of polyethylene terephthalate and polyethylene oxide, block copolymers containing polystyrene and poly-1,4-butadiene, and an ABA triblock copolymer made from poly-2-methyl-2-oxazoline, and polytetrahydrofuran. Other thermoplastic polymers, alinear, amorphous polynorbonon or organic-inorganic hybrid polymers consisting of polynorbonon units that are partially substituted by polyhedral oligosyls eskeoxane also have shape memory effect. Chemically cross-linked SMPs equals, the main limitation of physically cross-linked polymers for the shape memory application is irreversible deformation during memory programming due to the creep. The network polymer can be synthesized by either polymerization with multifunctional cross-linker or by subsequent cross-linking of a linear or branched polymer. They form insoluble materials which swell in certain solvents. Cross-linked polyurethane, this material can be made by using excess dissocyanate or by using a cross-linker such as glycerin, trimethylolpropane. Introduction of covalent cross-linking improves in creep, increase in recovery temperature and recovery window. PEO-based cross-linked SMPs, the PEO-PET block copolymers can be cross-linked by using maleic anhydride, glycerin or dimethyl-5-isophthalates as a cross-linking agent. The addition of 1.5 Wt% maleic anhydride increased in shape recovery from 35% to 65% and tensile strength from 3 to 5 MPa. Thermoplastic shape memory. While shape memory effects are traditionally limited to thermosetting plastics, some thermoplastic polymers, most notably PEEK, can be used as well. Light-induced SMPs. Light-activated shape memory polymers use processes of photo-cross-linking and photo-cleaving to change TG. Photo-cross-linking is achieved by using one wavelength of light, while a second wavelength of light reversibly cleaves the photo-cross-linked bonds. The effect achieved is that the material may be reversibly switched between an elastomer and a rigid polymer. Light does not change the temperature, only the cross-linking density within the material. For example, it has been reported that polymers containing ceramic groups can be fixed into predetermined shapes by UV light illumination and then recover their original shape when exposed to UV light of a different wavelength.